In this presentation, we will delve into the world of network performance optimization. It includes proven techniques designed to enhance network speed, improve reliability, and maximize efficiency. Let's begin this journey to supercharge your network. Before we dive into the solutions, let's identify the key challenges that often hinder optimal network performance. These can be broadly categorized into two main areas: infrastructure limitations and performance metrics. Under infrastructure challenges, we have bandwidth limitations, which is the maximum rate of data transfer across a network connection. Network congestion arises when the network carries more data than it can handle. Hardware bottlenecks occur when a particular component limits overall performance, and legacy system compatibility issues, which can restrict the adoption of newer, more efficient technologies. The second is the performance metrics. Latency refers to the delay before a transfer of data begins following an instruction for its transfer, and response time is the total time it takes for a system to react to a given input. Throughput is the actual rate of successful message delivery over a communication channel. Packet loss occurs when data packets fail to reach their destination, and connection reliability indicates the stability and consistency of network connections. Now let's explore some effective techniques for optimizing bandwidth usage. Two primary methods we'll examine are data compression and traffic shaping. Data compression is the process of reducing the size of data before transmission. This maximizes bandwidth efficiency by allowing more data to be sent within the same capacity. Here is an example of how to implement HTTP compression with gzip using Express.js. The code begins by requiring the Express and compression modules, then creates an Express application. To enable compression, it uses the app.use middleware, calling the compression function. Traffic shaping involves controlling network traffic to optimize bandwidth allocation. This ensures that critical applications receive the necessary bandwidth, while non-essential services are managed effectively. You can prioritize critical application traffic and implement quality of service, or QoS, to guarantee performance. Another thing is rate limiting for non-essential services, and bandwidth throttling during peak hours can prevent congestion and maintain optimal performance. Caching is a crucial strategy for improving network performance by storing and reusing frequently accessed data. Let's discuss browser caching and content delivery networks. Browser caching leverages HTTP headers to control client-side caching behavior. This reduces the need to retrieve resources from the server repeatedly, improving load times. To set HTTP cache headers in Express.js, you can use the response.set method. This example sets the cache control header to public maxage equals 86,400, instructing the browser to cache the resource for 1 day. The expires header is also set to 1 day in the future. Content delivery networks, or CDNs, distribute cached content across a global network of edge servers. This reduces latency by serving content from the nearest location to the user. CDN implementation offloads traffic from origin servers, reducing their load. It also provides protection against distributed denial of service, or DDoS, attacks and enhances security. CDNs work by caching content at edge servers. When a user requests content, it's served from the nearest edge server. If the content is not available on the edge server, it is fetched from the origin server and cached. Protocol optimization focuses on improving the efficiency of network communication protocols to reduce overhead and enhance performance. We'll look at HTTP version 2 versus HTTP version 1.1, and transport layer security optimization. HTTP version 2 is a modern protocol that offers significant improvements over HTTP version 1.1. Key differences include connections, where HTTP 1.1 uses multiple connections, while HTTP 2 uses a single multiplex connection. HTTP 2 uses compressed headers, whereas HTTP 1.1 uses plain text headers. Requests are sequential in HTTP 1.1, but concurrent in HTTP version 2. Finally, HTTP2 supports server push, which is not available in HTTP 1.1. Transport Layer Security, or TLS, optimization ensures secure connections without sacrificing performance. The latest TLS version 1.3 reduces handshake latency with one round-trip time. Session resumption reduces connection overhead by reusing previous session keys. Online Certificate Status Protocol, or OCSP, stapling eliminates the need for revocation checks. Optimize cipher suites balance security with speed by using algorithms with hardware acceleration. Here is a visual representation of a TLS version 1.31 round-trip time handshake. The client sends a client hello message to the server, and the server responds with the server hello along with the requested data, completing the handshake in a single round trip. Load balancing is a critical technique for distributing network traffic across multiple servers to prevent overload and ensure high availability. We'll discuss different load balancing methods and global server load balancing. There are multiple load balancing methods. First is round robin, which distributes traffic sequentially across servers. Least connections routes traffic to the server with the fewest active connections. Internet Protocol hash uses a hash of the client's IP address to ensure consistent routing to the same server. Weighted load balancing distributes traffic based on the capacity of each server. Global Server Load Balancing, or GSLB, distributes traffic across geographically dispersed data centers. It improves availability by redirecting traffic away from failed data centers. It also reduces latency by directing users to the nearest data center. And here is a visual representation of how GSLB works. Users from different geographic locations are directed to the nearest data center by the Global Server Load Balancer. This ensures optimal performance and availability, even in the event of a data center outage. Effective network monitoring and analysis are essential for identifying performance bottlenecks and ensuring optimal network operation. Let's look at key performance metrics and monitoring tools. There are the key performance metrics to monitor for network optimization. First, latency, measured by round-trip time, is the time it takes for a packet to travel from source to destination and back. Second is throughput, or bandwidth utilization, which is the actual rate of data transfer. Third is packet loss rate, which is the percentage of packets that fail to reach their destination. Next is connection time, which is the time it takes to establish a connection. And the last one is error rates, which are the number of errors during data transmission. There are many monitoring tools. Some of the basic network diagnostic tools includes ping, traceroute, netstat, and dump. Ping is used to test the reachability of a host on an internet protocol network. Traceroute displays the route and measures delays of packets across an internet protocol network. Netstat displays network connections, routing tables, and network interface statistics. Dump is a packet analyzer that captures and analyzes network traffic. This chart visually represents network traffic and latency over time. The traffic line shows the volume of data transmitted. The latency line shows the delay in data transmission. Balancing security and performance is crucial for maintaining a robust and efficient network. Let's discuss security measures that don't compromise speed and DDoS protection strategies. There are methods to achieve security without compromising speed. First, use TLS version 1.3 for faster secure connections. Implement HTTP Strict Transport Security, or HSTS. Enable session resumption to reduce handshake overhead. Use modern cipher suites with hardware acceleration and consider edge security solutions, such as CDN-based web application firewalls. To mitigate distributed denial of service or DDoS attacks while maintaining performance, there are certain steps to take. Implement rate limiting at the application layer. Use traffic filtering at the network edge. Deploy anycast networks for attack dilution and implement challenge-based verification during attacks. Here's an example of rate limiting configuration in Jinx. This configuration sets up a rate limiting zone that allows 1 request per second, with a burst of 5 requests. This helps protect against excessive request rates that can cause service disruptions. Here are key takeaways for network performance optimization. First is continuous monitoring. You should implement proactive monitoring systems to identify bottlenecks before they impact users. Set up alerts for performance thresholds and regularly review metrics. Use a multi-layered approach, where you can optimize at all network layers, from physical infrastructure to application protocols. Combine multiple techniques for compounding performance benefits. You should make data-driven decisions. Base optimization decisions on real performance data. Conduct A/B testing for major changes and measure impact on key metrics before full deployment. Use edge computing by moving computation closer to users by leveraging edge computing. Reduce latency by processing data near the source, rather than in centralized data centers. Conduct regular audits of network performance. Review configurations, update outdated protocols, and ensure alignment with current best practices. Use future-proofing to design networks with scalability in mind. Implement infrastructure that can adapt to increasing traffic demands and emerging technologies. Remember, network optimization is an ongoing process, not a one-time task. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.